Hello, we are Group 1, and now we will talk about the codes about this M3 hackathon, final hackathon. First, we import some package that can be useful for our later coding, and then we read in the training data and testing data, and we name it as train and test. And then we create a correlation matrix, which shows the correlation between each variables. And we notice that the correlation is really low, so we can anticipate that the R square should not be very high. And then uh, we use we transform the longitude and altitude to bins. So this code runs latitude and longitude to two decimal places, effectively grouping nearby locations into larger geographic bins. This reduces noise, prevents overfitting, and improves model generalization. By converting fine-grained location data into broader regions, the model learns regional data trains rather than memorizing exact positions, making it more robust and efficient. And then we create new features to enhance the model's understanding of rental dynamics. It calculates the average availability and the listing density, and helping capture regional trends. It also derives longitude-based availability and host density, um, and finally, it computes a demand score. So these features help the model better predict pricing by incorporating geographic and demand-related insights. And then we analyze and optimize the dataset. The column summary function generates a summary of each column, including data type, missing values, and distinct values, helping us understand the data structure. And we use the reduce memory usage function to reduce memory consumption by converting the float 64 and int 64 columns to float 32 and int 32, improving efficiency for large data sets. Then we prepare the data for machine learning by cleaning, transforming, and splitting it. It removes irrelevant columns, separates numerical and categorical features, and applies pre-processing. This dataset is then split into training and validation sets, ensuring consistency for model training. And then we run a PyCaret to check which model has the best performance. And we found that the light gradient boosting machine model has the lowest MSE and the lowest RMSE, as well as the highest R score. So this is the best model. And we also find that the gradient boosting regressor has the lowest RMSLE. So that's also a good model. So first, we take a look at the gradient boosting regressor and train it. And we find that it fits the model very well, and the model's performance is assessed using MSE. And we find that the MSE is about 0.185. So it's not so high.
And then I'm gonna walk you through a regression analysis using the light GBM, focusing on how we can enhance the performance through feature selection and cross-validation. So we began by setting up a light GBM regressor. We configure the model with 200 estimators and a learning rate of 0.1. So to ensure we only use the most relevant features, we apply recursive feature elimination. So this technique systematically removes less important features until we return the top 110 features. The selection process helps eliminate noise, reducing overfitting while keeping essential predictors. And after feature selection, we train a new light GBM model on the refined data set and validate it using the tenfold cross-validation. This ensures our model is not overfitting and performs well on the unseen data. Once the model is trained, we make predictions on the validation data set and evaluate the model using MSE, RMSE, and R-square score. And then to visually access the performance, we plot actual and predicted values. Ideally, our points should align with the diagonal line indicating the perfect predictions. So that basically is the closer our scatter points are to the line, the better our model performance. And we also generate a learning curve based on the result. And to conclude, this approach optimizes feature selection, leading to a more efficient and accurate light GBM requester. So by implementing RFE and cross-validation, we ensure a robust model that generalizes well to the unseen data. But for better improving the model, we also implement the hyperparameter tuning. So when training a machine learning model, we can instead of manually adjusting the values, we use the randomized search CV, which will efficiently test different parameter combinations to find the best configuration. And in our tuning process, we focus on optimizing the key hyperparameters for our light GBM requester, including the number of estimators, the learning rate, the tree depth and number of leaves, the subsampling and column sampling, and the minimum child samples. By running 10 randomized iterations with threefold cross-validations, we identify the best hyperparameter set that minimize the MSE and also with the RMSE. And once we train the model using the best tuned parameter, we evaluate its performance. However, despite the tuning process, the new model did not outperform the original model. So that means the MSE was slightly higher than the initial model and the R-square was lower. So this result highlights how our tuning does not always guarantee a better model. So we still keep to the original configuration that provides the best balance between bias and variance. And after comparing both models, we made strategic decision to keep our original model because it performed better in terms of the score of RMSE and accuracy and stability. And that's it.
Thank you.